Hello, welcome to this edition of Math Teacher to Go. Today we're going to look at some basic function shifting rules. My name is Patricia Doobie, and we will look at shifting vertically, horizontally, reflecting over the x-axis, reflecting over the y-axis, and combinations of shifts as well as stretches. So what you see in front of you is a graph of an absolute value function. I've chosen this function to be our example because it is very easy to see when this vertex moves. That's the point you'll be looking at, but you'll also see some changes in the steepness of the lines and things like that. So it gives you a visual representation pretty quickly of what we have changed. So the function is absolute value of x, and you can see that over here. Then the first thing I want to look at is a vertical shift. Now what you have to keep remembering is that when I say f of x, I mean here's how you find y when you know x. So this has an equals y there that you don't, that's implied. The f of x implies that. So in this next function below it, I've got an f of x plus c, and I haven't, right now c is 0. What happens when I let that equal y instead is what we're going to look at. So down here I have a slider, and when I move this slider, it changes the value of c. So now this value of c is right there. It becomes negative. When c is -3, what you can observe is that the red graph, which is f of x plus c, that's how you're finding y for the red graph, is 3 below the blue graph. Well, one way to make sense of that is the old way you found y was here. Y is the absolute value of x. And now the new way you're finding it is you're finding the old y and then you're adding some number. Well, in this case we're adding a negative number, and so your new y values will be changed by this amount. So they're lowered by 3, and that gives you the result of having the red graph. Every point in the red graph is 3 lower than the blue graph. If you had written out a list of points for your original blue graph and simply subtracted 3 from each of the y coordinates and plotted those, you would get the red graph. So if I change that to a positive c to be a positive number, you can see the red graph rises above the blue graph. So if c is positive and it's added to the end, you're just adding to the y value, so you're making everything a little higher. So let's look at what happens if I put the c in a different place. And I'm going to use that same c. Now I'm going to move this back now and make it 0 again and turn this graph on. Now we have a green graph. Right now it's sitting right on top of our blue graph because I have f of x plus 0. When the number is grouped with the x, as this is inside of parentheses, it changes or controls the x-coordinate. X-coordinates control where your graph is positioned horizontally, side to side. So what happens when I change this c? I'm going to make it a positive 2. Well, let's look. The green graph is the new one, but it looks like it's 2 to the left of the blue graph. That is true. When you group the plus c with the x, it does the opposite of what you think. Anytime you group a constant with the independent variable or x, it does the opposite of what you would expect. In this case, you would have expected the x's to go up by an amount of c, or 2 in this case, but they actually are reduced by c. You take 2 away. So the function f of x plus f of parentheses x plus 2 is shifted 2 to the left of the function f of x. So if I go up to this graph here and type a plus 2, we should see, oh, okay, so yeah, I'm still shifting the original f of x. So the blue one is now where the green one was, and the green one is 2 more to the left. But this is how I would, in this case, because the absolute values symbols behave like parentheses as far as grouping goes, this is absolute value of x shifted 2 to the left. If I want to shift 2 to the right, I'm going to take it away from there and go back to my original. So if I want to shift 2 to the right here, when c was positive 2, it shifted to the left. When c was, and so c needs to be negative 2 to shift to the right. So now my green function is 2 to the right of my blue function, and this would be f of x minus 2, or the absolute value of x minus 2, all inside the absolute value signs. So the horizontal shifts are tricky only because they don't do what you expect. They do the opposite. But the vertical shifts do what you expect. Here's the red graph, f of x minus 2 shifted down 2. So what you're seeing here is the difference in these functions. This blue one is f of x. The red one is f of x minus 2 on the outside. And the green one, I don't have a green marker handy here, so let me just do it in blue again. This green one here is f of x minus 2. And notice the green and the red overlap right here. That's kind of coincidental. If I had chosen numbers, one of them made them one of them something besides 2, it wouldn't have. But the green function is actually sitting here on top of the red function on the right. There it is. So you can always rewind this video if you wanted to see those again, but that's the difference between putting a number outside of the function or a number in with the function. And in this case, in with the function would be within the absolute value. Outside would be outside of the absolute value. And that's when you're adding or subtracting either to x or to y. When you're outside of the original function, you're adding or subtracting from y. When you're inside of the original function, you're adding or subtracting to x. And the reason it moves in the opposite direction is when this is f of x plus 2, you're saying go to the old function. So if x is 1, you say go to the old function to find out what the y value is 3, but this time graph it at 1, because 1 plus 3 would be 2. So if you want f of 3, you're really graphing. I said that backwards, didn't I? All right, well, rewind the tape there, but it's because you're moving to, if this is x minus 2, you're going to 2 to the left and graphing that where you are at x now. You're going to the old function, 2 to the left. So if your x was 3, in the old function you would go to f of 1, but you would graph it at x is 3, because 3 minus 2 is 1. That's why it moves it in the opposite direction. We worked with that in class a little bit the other day. The more you do this, the more you'll see that happen. If you write out tables of points, you'll see that happen too. So here is a different scenario. Let me shut these two variations off. What if the number is outside? Now I have a negative 2 there. Let me make that a 1 in this case. So in this case, function 6 here is the same as function 1 for the moment because c is 1. Now I'm multiplying, but what I'm multiplying is my old y values. So whatever I multiply by is going to change the y values by multiplying them by that much. If this is a number bigger than 1 in positive, my graph is going to rise quicker. If it's a number smaller than 1 in positive, between 0 and 1, it's going to make my graph rise slower. So let's see what happens. Let's make that a 2 or 3. There we go. There's a 3. Now you can see the purple function rises quicker. The vertex doesn't change. It stays at 0, 0. We call that the vertex, the point where the function turns around in an absolute value. It stays there, but it rises quicker because you multiply each. If c is 3, you're multiplying each old y coordinate by 3 and keeping the x coordinates the same. Now, if c is a positive number but not bigger than 1, let's make c 0.7, what you see is the purple function is actually just a little bit lower than the blue function. Well, that's because each y value gets multiplied by 0.7, which makes it smaller than it used to be. So it makes the slope a little less steep on both sides. So that's what happens when you multiply out in front of the entire function. You change the y values by multiplying by that much. Now let me put this back to a 1 so we don't get confused when we look at the next graph. Okay, so the next way we can change is by multiplying the x by something within the parentheses. Now, this is going to affect horizontal movement of the graph because you're doing something to the x. In order to do something to the y, you have to be doing it to the entire function. Here we're just working with the x. Right now that c is a 1, so it's f of 1x, which is the same as what we have in the original. So when I make c a 2, you might expect that the x value is all double and it kind of moves to the, stretches out to the right, but let's see what happens. Oh, wait a minute, when c goes up, it doesn't stretch to the right. So what I used to graph in my old function, when I graphed at x is 2, I had the point 2, 2. Now I have the point 1, 2 on my new graph. The point 0, 0 remains unchanged because if I multiply or divide 0 by something, it doesn't change it. It's still 0. But what I used to have in my old graph, I used to have a point at negative 2, negative 2, 2. That point is now at negative 1, 2. So all of the x's, if I take the points from my old function, if I take 0, 0, 1, 1, 2, 2, 3, 3, negative 1, 1, negative 2, 2, negative 3, 3, and divide each of the x coordinates by 2, I get my new graph. You might think you want to multiply because it's f of 2x, but you don't. You want to divide because anytime something is done to the x, you do the opposite of what you would think. So what if I make, let me look at shift doing this. What if I make this a negative 1? What happens? In this case, nothing. What a negative 1 does is it rotates you around the y-axis, and because of the symmetry of this, that's the only misfortune of having chosen absolute value. Because of the symmetry of this, it rotates around. But if I look at my graph of when I multiply outside, multiplying by a negative 1, if you multiply the whole function, it reflects you over the x-axis. So if I multiply the y's by negative 1, it flips my graph over the x-axis. If I multiply just my x's by a negative 1, it flips my graph over the y-axis. Okay, now let's look at what happens when we start to combine some shifts. Well, I guess we haven't really looked at this in depth as far as the vertical shift. So let's go back to what happens when the number is in front of the y. Now, what if the number is positive? Well, we did that. Anytime the number is negative, it has the effect of flipping and changing the y-coordinate by a factor. You multiply the y-coordinate. In this case, I've got c as negative 0.7. So the y-coordinate of the old function gets multiplied by negative 0.7, which is what flips it and changes the slope of the graph. When I go to what happens when I have the x-coordinate changed, well, if it's negative, it rotates. You can't see it, but it's rotated around the x-axis. You don't see it because of the symmetry. If I change this to an x cubed for one moment, it will show you the difference. So y equals x cubed is this blue one. You can't, and then f of negative 0.7 x cubed is this one. If I move that, you can see the green one is lined up kind of because the c is positive. I'm multiplying the c by the x, and what happens is when I put a negative in front of that, I rotate around the y-axis. This green one is positive on the left and negative on the right, which is the opposite of my original blue function. Let me go back to my absolute value function. It's not liking that. There we go. Okay, so these are interesting, but what's more interesting is what happens if we do more than one at a time. So I'm going to shut off this function and turn on this one, and now I have a new red absolute value function. it's still based in absolute value because I said it's negative 2 times f of x minus 1 plus 4. F of x is still the absolute value here. So when I graph that, what do? You have to work from the inside out. So I start from the inside, and the first thing I do is I take my blue function and I shift it 1 to the right. I would take this point here and move it 1 to the right, and do that for every point. You could do that to the whole graph at once if you see that visually, or you could do it point by point. Then I move my way outside and I multiply. Now what am I multiplying? I'm taking all the y coordinates, which I haven't changed yet because I only shifted to the right, by negative 2. So I multiply all my y coordinates by negative 2, and just doing that step alone without the plus 4 gives me that. And then I add the 4. So you can do these a step at a time. Look at each movement as its own individual step, but you have to do them in the right order when they're compounded like this. So let's go to the more generic form. What are all the things I could do to my absolute value function now? Well, right now I've set up some different parameters. A is the number I multiply by f of x, b is the number I multiply by x, d is the number I add to x, g is the number I add to f of x. So I've set them up to be just the basic absolute function now. If a is 1, I'm not changing the y coordinates. If b is 1, I'm not stretching in the horizontal direction. If d is 0, I'm not adding or subtracting anything, so I'm not moving left or right. And if g is 0, I'm not moving up or down. Let's take and see what happens when I change a to a negative number. Unfortunately, it's not working. I don't know why that's not working. I'm seeing it as just a line, a 0 line there. bx plus dg. Well, let me start playing with it differently here. Let's do just f of negative 3x. I'm going to change the color of this too. I thought I could change the color. But this is my new function. All I did was I did negative 3x. You can't see the negative because of the symmetry. If I now multiply that by a negative 2, all of a sudden my function is flipped over the x-axis. Now if I add 4, I've moved up. Now, we're not going to deal with what happens if I do a negative 5 here. Whoops, I did an equals 5. That's confusing. Negative 5 here, because it turns out you don't shift 5 to the right. You shift negative 5. You shift 5 over negative 3. You end up shifting 5/3 to the left. So if I take that negative 3 away, it'll be what we're doing. Okay, so if there's no multiplier in front of the x, that's as complicated as we get. When you do sine and cosine functions, you will have numbers in front of the x here, as well as adding. That gives you what they call a phase shift. But now what's happened is I've moved my x coordinates 5 to the right, and then I've multiplied them by a negative 2. And then, so the multiplying by negative 2 step looks like that, and then I've added 4. So I will put a copy of this, or a link to this particular graph that you could play with by changing these numbers around. I'm not sure why my sliders didn't work there. But you can change these numbers around and play with it yourself. But the other thing you can do is you can change the function. What if I change this to be, we looked at x cubed, what if I change this to be x squared? So I use the little, there's a couple ways to get the x squared, but I use the caret above the 6. So if I change this to be x squared, the shifting is still the same, the shape just changes. If I change that to be x cubed, the shifting is still the same, but the shape changes. Notice it remains the shape of the original function. If I do square root of x, which I think is obtainable down here, here's my original square root of x function, and now I'm looking at this fancy function there, but I could also just play with the slider. I could shut this off, and I can play with this slider. If I turn this on, I can see that when I change the amount I subtract, it keeps the same shape. It moves up and down. If I turn this on instead, when I change the amount in the x-coordinate, it controls the left-right motion. And when I change the amount in front of the function, if I make that big, it gets much steeper. If I make it negative, it goes the other way. And if I make it smaller but positive, it's not as steep. And if I choose to put the number right in front of the x, what we're going to find is the steepness changes, but it changes because in this case, I'm dividing all the x-coordinates by 2. So in the blue function, what was graphed at x is 2 is now graphed at x is 1. If I could get there. So you'll see that what was at x is 2 before is now graphed at x is 1. And that's why it looks like it makes it steeper. So I encourage you to play with this. I encourage you to go in and do the homework related to this. And this is really the summary of all the function shifting we'll do here. Like I said, in pre-calc 2 and trigonometry, you will get to put numbers in front of both the x and subtract from it, and we'll call it a phase shift. That's the only additional thing. But this works for every function you learn. These patterns hold for every function you learn, which is why they're so important. Okay, well, thank you for joining me in this edition of Math Teacher to Go. And rewind if you need to see things over again. Email me if you have any questions. Good day.